Hello Year 12 and welcome to our video on giant structures. You'll notice I started this video by putting a picture of a diamond and of Hagrid. Hagrid because he's a popular giant, though he is only half giant, and diamond because it is another very popular giant, though that is fully giant. I'm going to find out why today. Before we start this, it might be a nice idea to revise some of your stuff from GCSE on structures bonding. So think about looking at what a covalent bond is and what an ionic bond is. But I have put in a little bit of revision for that here. So without further ado, here are the specification points. Quite a few of these, but you'll notice that a lot of them are things that you're going to have to do in an exam rather than things you're going to have to learn. Though, that said, these are still things you have to learn. To learn to be able to apply these, apply this knowledge, learn how to apply these skills, and that's something we're going to focus on in class. Okay, let's start off with just recapping what ionic bonding is. If you remember, everything when it's forming a bond wants to have a full outer shell. Sometimes we form covalent bonds where we share electrons between two things that both nearly have a full shell, and sometimes we form ionic bonds between something that only has one extra electron, like sodium, and something that needs only one extra electron, like chlorine. So sodium simply gives its electron to chlorine to form a positive and a negative ion. These two oppositely charged things, ions if you will, have an electrostatic attraction between them. That electrostatic attraction, the size of that attraction depends on the charge density, which comes from the size of the ion, and the actual charge itself. So if sodium had lost 2 electrons, so like magnesium does, and formed Mg2+, it would have a higher charge density because it would be small and it would be pulling things towards it harder because it has a higher charge and therefore a higher electrostatic attraction. Anyway, what about in metals? Metals, the types of bonding we've seen so far, covalent bonding and ionic bonding, both require something that has nearly a full shell of electrons in order to do it. So you need a non-metal in both of them. You don't have that in a metal, but they're solid. They're not. Oh, there you go. Sorry. It's important that ionic bonds do not have directions like covalent bonds do. Covalent bonds, you can draw a stick and work out an angle between them. You can't do that with ionic bonds. They are everywhere. But back to metals. So, why are metals hard to melt? Well, metals only require the loss of a few electrons to form ions. That's one of the things that defines them. So, to gain a state arrangement when they are on their own, they break apart with the electron and form a sort of ionic bond with it. I say kind of because an ionic bond we just learned was between two oppositely charged ions, whereas an electron is not an ion, it is a subatomic particle. So, this electrostatic bond between the electron and the ion, the metal ion. That sounds quite confusing. Let me just show you it a bit more simply. So lithium has 1 electron in its outer shell. It wants to get rid of that. It's not happy having that 1 electron flying around in a shell that's designed for 8 electrons. It seems a little bit wasteful. So what it does is it gives that electron away, and it forms an electrostatic bond between them. The electron and the ion are still attracted to each other, but they are not actually part of the same atom anymore. All of the other lithiums do that, so then we end up with this bond between the sea of electrons, which is where all the electrons have gone. They're delocalized between the lithium ions. Delocalized means they're not stuck on any particular atom. The bond is between the lithium ions and the electrons in this electron sea. We're going to talk about it a little bit more later, so don't worry if it hasn't really sunk in yet. But essentially it's a bond between a lithium ion and an electron that does not involve them sitting together in the same atom. Okay. When we're talking about solid state chemistry, or what solids look like, we always refer to lattices. Now, a lattice is just a regular arrangement of points. You can have a lattice that is a piece of garden thing that you put plants to grow on. You can have a lattice in a pie, lattice in the structure of sodium chloride. It's just a repeating selection of points. So this lattice, if you look here, that is the same as this bit over here, is the same as this bit over here. It repeats all the way across the pie. Same as this, same as this. So we use a lattice to describe the structure of a compound because there's too many atoms to draw the whole thing. We draw a bit of it and we say this is going to be the same for everything else in this compound. First sort of lattice we're going to look at is called the giant covalent lattice. And it's called giant covalent to contrast between giant covalent and simple molecular. Sometimes it's called giant molecular. And essentially, if we think of a simple molecular compound as something like water, a giant molecular compound is essentially that, just a giant molecule. Rather than just forming a couple of bonds, the bonds form across the whole molecule, and we have this huge structure like diamond, where we've got each carbon forming a bond to another carbon, to 4 other carbons, and then that carbon forming a bond to 4 other carbons, and that carrying on across the whole molecule. Same with silica. Silica is SiO2. You have silicon forming a bond to 4 different oxygens, each oxygen forming a bond to 2 silicons, and we get the similar structure to diamond. Silica, incidentally, is just sand. Graphite is a little bit different. When we're talking to you about that in a little bit more detail shortly. So, they have strong covalent bonds between each atom. This means they've got a high boiling point and melting point as well. In order to melt these compounds, you have to break apart all the atoms. Each atom's got 4 covalent bonds to it. That means it's really hard to pull it apart. None of them have any free electrons apart from graphite. This means they don't conduct electricity. In order to conduct electricity, you need some free electrons to move around and carry the electricity around. Only graphite can do this. Diamond and silica cannot. Try and pass an electric current through a diamond, you will find yourself looking very foolish. So what about graphite? Well, graphite has interesting properties because of its interesting structure. It forms layers. Each carbon bonds to 3 other carbons. That means each carbon is left with 1 extra electron that is not bonded covalently to any other carbons. So you have these layers, these sheets of carbons all bonded to each bonded to 3 other carbons, and then their spare electrons go in between 2 of the sheets. You have van der Waals bonds between the 2 sheets. Because the sheets are so massive, they're fairly strong. Not as strong as a covalent bonds, however. So that's why, when we are writing with pencils, we can use the graphite in our pencil to just rub off one of the layers and leave it on the paper, so that layer lasts on the paper, and that's what writing is when we use a pencil. Also, these electrons that live between the 2 layers are free. They can move around, so they can carry charge. So we can pass electricity through this layer, but we can't do it between the layers. That means graphite can conduct electricity in one direction, but not the other 2. Very interesting, very useful property of graphite. Anyone interested in the structure of graphite should probably look up graphene as well, a more recent structure made of carbon that's even more interesting. Okay, the other sort of thing we need to talk about is giant ionic. So when ions arrange themselves, they do it so that none of the like charges are near each other. We don't want a sodium plus to be next to a sodium plus. We don't want a chlorine minus to be next to a chlorine minus. So this is how we draw it for an NaCl. I'm going to be showing you in the lesson a couple of easy ways of drawing these things, but it was worth a practice. We do need to be able to draw what a giant ionic structure looks like. So every sodium in here has 6 chlorines around it, so one at the back, 1 at the front, and then 4 all the way around it, and every chlorine has the same. So we get this nice repeating pattern all the way through. There are no free electrons, so this ionic structure will not conduct electricity in a solid state. If you melt it, it will do, because the ions are free to move around and carry the charges. Okay. We also have 6 bonds for every ion there. This gives us a really high melting point. If you ever try melting salt, you'll find that it's very difficult. Finally, well, second to last, we're talking about giant metallic bonds, giant metallic structures. This is kind of similar to ionic, I've said, but not really. What we have here is we have the positive metal ions in a regular lattice. So the positive metal ions are in the same place. They are in a regular arrangement. But the electrons are really small, and they're not joined up to anything. So they can excuse me. They can move around freely however they like. You wouldn't find too many leaving positive ions that much, because you'd end up with a lot of repulsion. But they can move around, and they can carry electricity if they want to. Because we have these disjointed, these delocalized electrons, it also means we don't have directional bonds. So we can bend our metal quite easily. There's nothing forcing it into a certain shape. It's still got a high melting point though. And that's because these metallic bonds are actually quite strong. Anything between opposite ions is pretty strong. The melting point itself and the strength of the bonds depend on the number of electrons that are given to the electron C. So an atom that needs to lose more electrons to go to have a complete outer shell will have more electrons in the electron C, and therefore more bonds between it and the electron C per atom. Notice I'm talking about the electron C as like a separate thing that's bonded to the ions, and that's the best way of looking at it. Rather than thinking this ion is bonded to this individual electron, it's better to think of it as these ions, all of these ions are bonded to the whole electron C, because the electron C will not be constant. So the more electrons that we give to the C, the more bonds we have between it. The charge density on the atom means there'll be a higher electrostatic attraction, so we have a smaller atom that will be attracting the electrons to it more closely, and the charge as well. So if we have a more highly charged atom, it will also attract the electron C to it more strongly. Okay, always remember, if an atom forms a 2+ ion, you have to draw 2 electrons for every atom when you're drawing a picture of it. A lot of people lose a lot of marks in exams for not doing that. Finally, we need to think about what simple molecular compounds look like when they're in a solid state. So for example, solid water, or ice as some people call it, forms this structure here with hydrogen bonds forming kind of regular hexagons. I've got a big model of this in my lab which I'll show you on Wednesday, but you can have a little look at this and work out roughly what shape it's going to be. And then iodine is another one that's a solid at room temperature, and you can see it forms a kind of cubes with the atoms on opposite corners. Don't worry too much about this. You may not have to draw it. You don't really need to understand why it forms this, but essentially this is just the best arrangement for getting the most out of the van der Waals forces. So to sum up, let's look at where our properties come from, because that's what most of the questions are going to be about. They're going to be asking you to discuss why different materials, different solids have different properties, and that is what structure and bonding is all about explaining. So the structure, that's the shape and the way the bonding is in the molecule. It's the shape of where all the molecules are, where all the atoms are if it's an atomic structure, and how that looks across the whole lattice. So how many bonds are there per atom? The more bonds you have, the higher the melting point. Are the bonds directional? If you have directional bonds, like in diamond, then it will be hard. And if you don't have directional bonds, like in metals, it will be bendy. The exception to this is ionic bonding, because obviously ionic substances are quite hard. You can't bend a salt. They tend to crumble off into little crystals. And that's because we have so many bonds per atom, we can't really move things around. We don't want to have positive things near other positive things. Finally, are there free electrons, like in graphite or in metals? Because if there are, it will conduct electricity. What about bonding? Well, bonding is all about the strength of the bonds, and that tends to explain how some things have different lower melting points than others. In order to melt something, you need to break apart all of the molecules or atoms. The stronger the forces between these, the higher you need to heat it in order to do it, because you need to put more energy in to break the bonds. So, thinking about the strengths of bonding, covalent bonds tend to be the strongest, ionic bonds closely behind, followed by metallic bonds, followed by the sort of van der Waals, followed by hydrogen bonding, followed by dipole-dipole, followed by van der Waals. Metallic bonding is a little bit of an exception because it varies so much in strength depending on how many electrons we're donating to our electron C. I'm going to tweet another video that I saw a man called Hank Green do on this same topic that I think you might find interesting. By no means you have to watch this one as well, but it might add some extra things to your understanding. Please make sure the notes are done well so that we can fire straight into this in our lesson on Wednesday. Thanks very much. Bye.